Hello everyone, in this video we'll talk about lesson number 6 part 3, which will be over the orbital motion and the concept of centripetal force. And this will explain to us why the moon revolving around the earth does not fall toward the earth, why satellites and space stations do not fall, and also why planets around the sun do not fall into the sun, although there is gravity in all those cases that pull those planets toward the sun, that pull the moon toward the earth, and also that pull artificial satellites toward the earth. The secret to the orbital motion lies in the concept of free fall. And in order to understand that, let's look at this demonstration. Imagine a cannon firing a cannonball with high speed. Let's say, for example, you start with very low speed, let's say around 0.01 kilometer per second, and you can see the cannonball will fall directly toward the earth. Now let's give it higher speed here, around 2 kilometer per second, which is around 1.6 miles per second. And you can see in that case the cannonball will go further distance, but eventually it will fall toward the earth. Now let's give it more speed. Let's go to 4 kilometers per second, which is around 3.2 miles per second. And let's fire. And you can see the cannonball went further distance. Let's go to 6 kilometers per second. Reload and fire. And you can see here the cannonball went further. If you take it to 7, still hit the earth. Now after 7, let's go to 8, we'll see something interesting. Now the cannonball is falling toward the earth, but is falling in an orbit, meaning while it's falling toward the earth, its sideways velocity overcome the curvature of the earth, which keep it in a constant orbit. So actually the cannonball is falling toward the earth, but it's falling in an orbit. We call this velocity orbital velocity, which is the minimum velocity needed to put the object in an orbit around the earth. And its big velocity is 8 kilometers per second. And it depends on the distance between the object in orbit and the surface of the earth. 8 kilometers per second, which is equivalent to around 17,000 miles per hour, is almost the speed of the International Space Station around the earth, and the International Space Station is around 200 miles above the surface of the earth. If you need to go at higher altitudes, like the case of satellites, for example, satellites fly at a height of around 36,000 kilometers above the surface of the earth, and hence they need a much lower speed. Their speed is around 3 kilometers per second instead of 8 kilometers per second, and that will give them around 24-hour revolution time around the earth, which will keep it above specific spot over the earth. In the case of this cannonball, assuming it's at a height of around 300 kilometers above the earth, it will take it around 85 minutes to orbit the earth at this speed, 8 kilometers per second. In the case of launching a real satellite, this does not happen through a cannon like in the previous demonstration. This happens through a rocket. A rocket will be launched that basically carries that satellite with it, and this rocket will go through several stages. The first stage is to accelerate upward until it goes beyond the Earth's atmosphere, and then it will go through the second stage where it will tilt a little bit, then the third stage where it will take its orbital position, and that's when it releases the satellite with its initial speed of around 3 kilometers per second, if it's at around 36,000 kilometers above the earth. And the satellite will continue moving in an orbit around the earth since there is no air resistance. So now we understand that objects in orbit, they are actually falling toward the earth, but the reason they don't plummet The reason they don't hit the Earth is because of their sideway velocity that is very high, that keep them in orbit. And now we can understand why astronauts feel weightless. They're actually feeling weightless not because the lack of gravity. The astronauts in the International Space Station is around 200 miles above the surface of the Earth. That's around the distance between Tulsa and Houston, so they're not far away. They have exactly the same acceleration due to gravity as you and me, maybe a little bit less, but it's basically very close to 9.8 meters per second, so gravity is still acting on them. They still have weight, and their weight is equal to the mass times the acceleration due to gravity, but they appear to be weightless, and that's the key word. Apparent weightless is due to the fact that they are falling toward the Earth. When you fall, you feel weightless. To give you an example, assume you are in an elevator and you are standing on a scale, and the scale records your weight, and suddenly the elevator starts falling. What would be the reading on that scale? The reading on that scale will be 0. And that's because you don't feel any pressure from the Earth. You are in a free fall. So you appear to be weightless, although you are in a free fall. And that's exactly why astronauts in an orbit around the Earth feel weightless. This will bring us to the end of lesson number 6. Let's go over some of the questions. Question number 6 asks, does a force always produce motion? Now, in order for the force to produce motion, it has to be unbalanced, meaning the net force has to be more than 0. Sometimes the object could be subjected to several forces that cancel each other. Not all the forces will produce motion. It has to be unbalanced force or forces that have total of net force in certain direction, those that will produce motion and acceleration. Question number 7, in the absence of net force, an object will necessarily, so if there is no net force, meaning the total force of the object is 0, in that case, Newton's first law will come in action, meaning object will be either at rest or moving with a constant velocity, and that all constitutes 0 acceleration. So the answer will be have 0 acceleration, because 0 acceleration could be object at rest, or it could be object moving with a constant velocity. So the answer is C here. Question number 8, true or false, an object on the moon weighs 1/6 of the weight on the Earth, therefore the object has less inertia. Now remember, inertia has to do with the mass, and since the mass is the same whether you are on the Earth, the Sun, Moon, Jupiter, then the answer would be false. The mass will be the same. Your resistance to the motion will be the same whether you are on the Earth or the Moon. Question number 9 here is a very good example of Newton's first law, because when you hit the handle, the head of the hammer will be still moving because of the law of inertia, because Newton's first law, objects tend to continue moving in a straight line, and that will get it tightened to the handle. Question number 13, if you drop 10 pound and 1 pound rock, assuming the air resistance is negligible, they should fall at the same rate, meaning they have the same acceleration. Now don't confuse acceleration with the force due to gravity. We have the acceleration due to gravity, which has to do with how fast they fall and at what rate. And there is the force due to gravity. Now the force due to gravity on the 10 pounds is more than the 1 pound, because force due to gravity is equal to the mass times the acceleration. And the mass of the 10 pounds is more than the mass of a 1 pound rock. Meaning the 10 pound rock will hit the ground harder than the 1 pound rock. But that is independent upon the acceleration. The acceleration is 9.8 meters per second on the surface of the Earth. So both rocks will undergo the same acceleration. So the reason they have different weight and hence different force of gravity is due to the mass, not how fast they fall. If they drop on the surface of the moon has less gravity, around 1/6 the gravity of the Earth, so both of them will fall slower, but again they will fall at the same rate. Now here in question number 17, make sure in order to find the acceleration to convert the 7 grams to kilograms. That's by moving the decimal point 3 places to the left, because Newton is kilogram meter over second square. So in order for kilogram to cancel out with the kilogram of the mass, you have to convert the mass from gram to kilogram. In number 18, you are asked to find the weight in Newton. Now remember, the weight is the mass times the acceleration due to gravity. So you have to multiply 6 kilograms by 9.8 meter per second per second. In question number 19, you are asked to find the magnitude of the gravitational attraction, and here you have to use the equation force equal to G times the mass of the first object times the mass of the second object divided by the distance squared. G is constant, it's around 6.67 times 10 to the negative 11 Newton meter squared over kilogram squared. You have to multiply it by the mass of the first object, the mass of the second object, and then divide it by the distance squared. So you have to square the 0.15 meter and then carry out the calculation. In question number 20, how would the force of gravity change when the separation distance double in part A if it decreased by 1/2 in part B? We call the inverse square law. So if you double the distance, the force will decrease by the inverse of the factor squared. So double means you multiply the distance by 2, so the force will decrease by 1/2 squared, which means 1/4. Now in part B, if you decrease the distance by 1/2, the force will increase by the inverse of 1/2, which is 2 squared. So the force will increase 4 times. Now let's look at some of the questions in the homework. You remember the SI unit of Newton. Newton represents kilogram meter over second square. We talked about that in part 1 of lesson number 6. In question number 23, you are given the force 1500 Newton and you are given the acceleration 2.5 meter per second square. So to find the mass, we have to rearrange the equation to mass equal to force over acceleration. We talked about how to rearrange Newton's second law depending on what you are asked to find, including the mass. And we said the mass will be equal to the force divided by the acceleration. So you have to divide 1500 Newton by 2.5 meter per second per second. In question number 24, you are asked to find the weight in Newton of a 250 gram package of cereal. So what you need to do is to multiply the mass by the acceleration due to gravity. Weight is force of gravity, and force of gravity is the mass times G. G is 9.8. Make sure to convert the 250 grams to kilograms, and that's by moving the decimal point 3 places to the left, which will yield 0.25 kilograms. In question number 24, again, it's the inverse square law. So what happens when you decrease the distance between two objects by 2/3? So again, what you do to the force is the inverse square of the 2/3. The inverse of 2/3 is 3/2, and when you square 3/2, this will give you 9/4, which is around 2.25. So basically the force will increase by 2.25. Now if you increase the distance by a factor of 3, the force will decrease by 1/3 square, which is 1/9. So the force will decrease by 1/9. So this will bring us to the end of unit number 1. Please feel free to email me your questions. Thank you for watching.